Thank you for attending our webinar about the acoustic camera and an introduction to beamforming. My name is Rob Warmbold. I'm the product manager here at Polytec for the acoustic camera product line. Basically, we're going to go over the acoustic camera, the theory behind the technology, as well as the different product offerings we have for the acoustic camera. Basically, beamforming is relatively simple to understand. It is similar to the human hearing on how it works. As you can see here on this top chart, we have a noise source here with 4 different microphones or sensors. You can almost think of those as your ears, as if you would just snap on the left side of your head. It's going to hit your left ear before it'll hit your right ear. So this is what this is demonstrating here. We'll have a sound source at this point and the different microphones here. There's a runtime delay between the noise source hitting each of the microphones. What happens is, due to the runtime delay of the sound source hitting the microphones, you're going to have that impulse arrive at the microphones at different times. And this is what this is showing here. We have that same impulse, but due to the distance from the sound source that varies between microphones, it's going to hit the microphones at different times. What we do is we adjust that time, and we basically introduce a delay for each of those impulses and line them up here so that they essentially hit the microphones all at the same time. Once we do that, we sum them up, and then we normalize them based on the amount of microphones we have. What we do with that information is basically divide our image from our camera into different pixels. And at each pixel, we calculate the runtime delay for each of the pixels that are in the camera image. A good representation of this here is this video, basically showing how we calculate each of the pixels and then create a acoustic map of what we're seeing. This can be done in real time as well as in post-processing, looking at different pixels individually. As that last image shown, that was on a 2D plane. We can also transfer this into a 3D space. We either can use point clouds, meshes, or real CAD images. That way we can know the exact distance from each microphone to the surface of whatever we're mapping on. The principle is the same. We basically divide the CAD model into pixels as you would on the 2D, as you saw on the 2D image, and the theory is exactly the same. The acoustic camera was first introduced by GFAI in 1999. They were working with the DLR in Germany and realized that they had a product that they were able to commercialize. As you can see in these images, the technology has greatly improved over the years due to, cameras getting better. So on the left, you'll see an image back in 1997, pretty pixelated, blurry. But as time moved, technology gets better. We're able to now map, for example, in this image on the right, in 3D spaces. This is at a University of Michigan football stadium. You can obviously see that the student section is here on the right, with the spectrogram on the bottom showing all the impulses that we were measuring during this measurement here. As I said, over the years, there's been more advances in technology, calculation power. The computers were able to sample at 192 kilohertz over all channels simultaneously, which gives us great spatial resolution here. On the left, you'll see they have some microphones set up. They're looking at a plane passing overhead. That's one example of a use. On the right, you'll see a pass-by measurement on a car. The more channels you see basically allows for better spatial resolution as far as getting the side lobe patterns down. But we'll get into that more in a little bit here. An introduction to the array design. Ideally, if you would have ideal distribution of microphones, they would be an infinite number of microphones randomly distributed. But in practicality, that could get expensive, as you can imagine, having an infinite number of microphones. So basically, we have chosen different array designs as a best compromise to whether a particular application or ease of use. Basically, the goal is to have a sharp main lobe and weak side lobes. Side lobes will always exist, but they should also help you kind of locate a source. They can help point to a source, which I'll show you here in a second. But obviously, the best compromise is something that works for the application, is cost effective, and gives you results that you expect. This is our basic array geometries. Starting with top left, we have our ring arrays. Over the years, we've found that this is one of the most applicable to many applications. It is very easy to use, and the side lobe patterns are very helpful in pointing out a source that you may not know where it's coming from. You'll see in the next coming slides of what I mean by the side lobe patterns, but each array geometry will give a different side lobe pattern. And over the years, like I said, the ring has proved to be the most useful in pointing out these. The top right is a star array. This is generally used for free field measurements, larger distances or farther distances, lower frequencies, very useful for far field measurements. The sphere, bottom left, this is used for interior measurements, cabin measurements of cars, room and building acoustics. As you can see, it has microphones facing all opposing directions. Transparent, it's acoustically transparent, so you have no sound source doubling on the surface of the array as if it were a solid sphere. And then we also offer microphone bundles in which you can customize your own array. This is useful for specific applications where you have, maybe a specific problem that you're repeating all the time, and you can kind of customize it to fit your needs. A few points to consider in array design. If you know your expected frequencies, then you can account for that in your array design. As I mentioned before, the star array, for example, is good for lower frequencies. The theory behind that is basically the lower the frequency, the larger the wavelength. So in order to capture that wavelength, you need to have far opposing microphones at a far spacing. So on that star array, when it's opened up, the diameter is 3.5 meters. For example, if you're looking at a sound wave at 100 hertz, the physical wavelength of, the physical size of the wavelength is 3.4 meters, so we are able to catch that with the farthest opposing microphones there. If you're looking at higher frequencies, then you're going to have closely spaced microphones. So like in our ring array, you'll see the microphones are a bit closer together. We're able to go a bit higher in frequencies when you're looking at like 10 kilohertz or above. Another point to consider is to try to create sharp main lobes and minimal side lobes. That way you're able to pick out the sound source exactly where it's coming from. Spatial resolution does not have to do with the amount of microphones, but more on the sampling rate that you take the data at. As I mentioned earlier, we do 192 kilohertz over all channels simultaneously. This gives us extremely good spatial resolution, down to the millimeters even, depending on what frequencies you're looking at. But that is something to consider. The more channels you add will minimize the side lobe patterns. And I can show you that. I have some examples in the coming slides there too. And then obviously you got to consider if you're looking at a 2D or 3D application. As I mentioned, the sphere array with the opposing microphones, that is used for our 3D applications. Our ring array, they're all pointing forward. So we know we're going to assume a measurement plane based on the camera image. And then obviously your size and distance of the measurement object, you want to be able to see that all in your camera image. So as mentioned, your array geometry will produce different side lobe patterns. When looking at the ring array, you'll see you kind of get a ring pattern, as if maybe you throw a pebble into a pond, you get the ring pattern coming from the position of where the stone hit in the water. And that's similar to what you'll see in the ring with the side lobes, which help pointing you to the sound source. Maybe if you have some ring pattern coming from off your image, you can kind of determine that maybe your actual sound source is actually off your image, and you can use those ring patterns, those ripples, to kind of point you into that direction. Looking at the star, it has its own unique side lobe pattern there. You can clearly see the three arms of the star array. And then looking with the sphere array as a 2D image, you'll see the image that it produces, or the side lobes that it produces there. As mentioned earlier, sampling rate is what will produce your spatial resolution, or enhance your spatial resolution, I should say. On the left, you'll see we're looking at sound source 1 meter away. The sound source, there's actually two sound sources there that are 1 centimeter apart. Those are represented with the two little red dots. On the far left, we have 16 channels. We're sampling at 48 kilohertz. And you can see the sources. You can kind of tell there's two sources, but they're not clearly defined as two sources. As we double the channel count, you'll see that the sound sources themselves didn't get any clearer, or didn't basically separate or distinguish themselves. The only thing that happened is your side lobe patterns were reduced. And add double the channels again on the far right, still sampling at 48 kilohertz. All that happened was sound lobes, or the side lobes, had vanished. Now looking at a sampling rate of 192 kilohertz, the same sources separated by 1 centimeter at a meter's distance, you can clearly see them differentiated. There's two sound sources clearly visible by those little red yellow dots there. Adding more channels as we go to the right. So the middle picture, we've got 32 microphones now. Once again, sound sources are still clearly visible, just side lobes have been reduced. And furthermore, on the far right, with adding the 72 channels now, sound sources are still clearly visible. So with focus distance, this is one thing you have to take in consideration when doing your measurements. The acoustic camera doesn't know how far an object is. That's something that you'll set in your measurement prior to your measurement, basically a focus distance. With the ring array, the sphere array, all the 2D arrays, basically you're assuming a measurement plane, which is your camera image. And like I said, we basically take that measurement plane, the camera image, and separate it into pixels. So the sound level, the sound pressure level of the acoustic map will be basically correct at 1 meter is the sweet spot for all of them. It'll be 100% correct at 1 meter. With the wrong focus, you'll get basically incorrect levels due to the algorithms and it calculating within the software. But this effect varies by frequency and array shape. The ring array shows least sensitivity to focus distance. But with some of the other arrays, you got to be careful with setting your focus distance correctly. So now I'll talk about some typical beamforming applications. I mean, basically beamforming or acoustic cameras can be used for anything where you're trying to localize a sound source. So these are just some of the typical applications we've seen. Aerospace industry, obviously they're trying to lower sound sources on airplanes for environmental concerns and overhead passages of the airplanes coming from concerns from the community or whatnot. Then automotive industry, we're seeing a lot more now as we're moving into electric vehicles. Your typical sound sources from a combustion engine are no longer there, which now uncover sources that were previously masked by the combustion engine. So that's been a big push lately. Consumer products, always, no one wants a noisy product or annoying noise coming from a product. We've got environmental applications, you got loud sources at manufacturing plants that may be a concern to the community. Railway industry, room and building acoustics, and even zoological applications, studying animals and how they communicate. But basically, like I said, all audible sounds can be recorded, mapped, and analyzed. So if you're looking for a sound source that you are not sure where it's coming from, the acoustic camera is a perfect product and solution for this. This is an example of a hard drive measurement, pretty small object here. They were looking at this the read-write drive essentially inside it, and you can see a point source clearly visible here by this red dot here. On the top, this is your typical post-processing view. You'll see this top panel here, window, is what we call channel data. If you were to zoom in on this is basically 48 channels, 48 channels of each microphone, basically overlaid on top of each other, and that's your raw data. From there, we can create a spectrogram down here. So we've got frequency on the left, time on the bottom, all mapped accordingly to dB. What happened here is they highlighted this section here. As you can see, there was a click of some sort. They highlighted it, and they're just mapping this area that is highlighted, which is represented here on the image. Another application, we've done a big installation at Porsche in Germany at their R&D center. This installation had a 500 plus channel array. You can see on the right here, we've got a panel of microphones. There's another one here, and actually off this image, there's one right above. And what we're able to do is map on a 3D image of the car. This right here is looking from the top panel in 2D, but they're able to throw a 3D model in there. And since we have microphones on all sides of the car in this wind tunnel, they can do mapping on a 3D image of the car here. This is pretty impressive. The sound sources they're able to see. They've taped a piece of a tape essentially on one of the mirrors, and they were able to pick that out in a wind tunnel, which is quite amazing, and that's due to the sampling rate of the system. Another application, also a wind tunnel. This one is showing basically the correlation of a sound source on the outside of the vehicle and how that is transmitted to the inside interior of the vehicle. They use two different arrays simultaneously in this measurement. We have that one array you can see up here on the outside, and they also had the sphere array on the inside of the car, and they're basically cross-correlation between the outside sources and what is heard inside the vehicle. Another automotive application, buzz, squeak, and rattle. We all had that annoying squeak inside your car and you just can't figure it out. And this is one of those applications here. Customers complaining about a noise, they couldn't figure out where it was coming from. They did a quick measurement and they basically found that there was a loose bolt under the driver's seat here that can be seen on this image down here. Also, they had some noise coming from the sunroof. The sealing up here wasn't sealing correctly, and they got some rattle from the sunroof. And you can see that on the 3D image of this car right here and here, which represent the left and right side of the sunroof. There's also psychoacoustics that we can get into. Not always is the loudest sound source the most annoying sound source. Human hearing perceives different sources as more annoying than some others. Just because it's loud doesn't mean it's the most of concern. So we can do different parameters in psychoacoustics from loudness, sharpness, roughness, and map those accordingly. Here's one of our far field applications. This was a mining conveyor belt. We were using the star array. They were looking at if they could basically determine if a bearing on this conveyor belt was going out. And as you can see on this mapping, they were easily able to pinpoint, looks like two different sound sources on this conveyor belt that were giving them issues as far as preventative maintenance. Here's another measurement used where the star array was used. They're looking at obviously a wind turbine here. They are quite loud, and they're doing a study on how they can basically reduce the noise that these blades are producing. So you can see we've got a video that we can map in real time, essentially, looking at each of the blade passes. This here was a room and building acoustics application. They were demonstrating basically how the sound was traveling through the Coliseum here. What they used was a balloon and popped a balloon to create an impulse, and then mapped it and how it played out through the sound field of the Coliseum here. Another room and building acoustics, they're looking at leakage from a window. Pretty simple application, but they played white noise outside the window, and you can easily see the leakage coming from the top of the window when it was tilted open. Even when it was closed, we're able to see it. leaking through the top there. This is a new product. We just came out with it this year. It is our new handheld acoustic camera. This one has 96 MEMS microphones on the front. You can see each of the little holes here represents a microphone channel. It is completely standalone. We've got a battery down here on the bottom. It's ran on a tablet, Microsoft Surface. Quick and easy to use, point and shoot. It'll eventually include a 3D scanner, so not only will you get the sound mapping, but you can also get a 3D CAD model by going around the image and then mapping on that 3D model. It'll also have holography capabilities when you're looking at lower frequencies, basically structural born noise sources, and that'll be one of its abilities as well. Very easy to use. You can pull measurements from this into the full version of the software and do your post-processing on your PC. So you don't have, it's not just tablet-based. You can bring any measurement into any noise image software. Some other product offerings we have beyond beamforming is some holography arrays. This is a 120 channel Fibonacci array. It's capable of both holography and beamforming. Hence why it has two cameras. One camera is used for beamforming and more far field measurement, and the other camera is more of a fisheye lens for the near field holography measurements. We also have acoustic intensity arrays, which you'll see here in the middle. What we're looking at there, we have microphones on the front, as well as each microphone on the front has an opposing facing microphone on the back of it, which gives us the ability to map acoustic intensity. And then, as mentioned before, we can also do custom arrays based on your application. You saw that in the Porsche application, that was completely custom install, but we can do basically any microphone geometry array, however you want, that fits your application. Thank you for attending, and I hope to see you guys soon.